Today we will talk about wavefronts and interference. Those are two concepts that are very important when it comes to propagation, which is the overall topic of this unit. The learning objectives are to first understand the concept of wavefronts, and we should be able to define a wavefront and then to manipulate it mathematically. And then once we have one wavefront, we should be able to add it with another wavefront, and this is where the concept of interference comes in, and we should be comfortable with defining the conditions for where wavefronts add constructively and where they add destructively. To define a wavefront, it is a set of points that through propagation has accrued the same amount of phase. One example was brought up in previous lecture. It was that of plane waves, and as the name suggests, the wavefronts are planes, and as plane waves propagate, we have electric field in purple and magnetic field in red. Together with the propagation vector beta, they form a right-hand rule: electric field, magnetic field, propagation. And as the plane wave propagates, what we have is a changing electric field and a changing magnetic field. And as you can see, electric field goes down and then goes back up, and similar for magnetic field. When we talk about interference, we will need to take note of those maxima and minima, and we will, for example, in this case for electric field, define maxima as red wavefronts and minima as purple wavefronts. Conceptually, it might be easier for us, or at least more intuitively, to talk about wavefronts and interference in terms of a lens or in terms of imaging in optics. A lens is shown here, and on the left side we have a diverging spherical wave, and on the right hand side of the lens we have a collapsing spherical wave. And what the lens does is it converts one set of wavefronts into another set of wavefronts. What this means in terms of things that are commonly understood by us is that if you look inside of your eye, there is a lens. And what you can understand this to be is an object, a distant object, for example, a star. And what a star emits is a set of spherical waves that take a while to propagate, and in reality, it'll be much further to the left of the lens, but whatever spherical waves that it emits will focus down on your retina and form a point, and that point your eye will detect as the star. In reality, of course, we have not just one star, but we have a plurality of sources, and each one of those sources produces multiple wavefronts that interfere together. And if we look in the context of the same lens, we can have one object slightly off axis, and those red lines once again show the maximal points of sine or our cosine wave, and similarly it will convert one set of divergent spherical waves into another set of collapsing spherical waves. Next, we can have 2 points, and we can image the one above to the one below on the detector, and the one below to the one above the detector. And similarly, the lens will map both wavefronts simultaneously from one point to the next. The interesting thing you can note happens around this optical axis, where the red lines intersect with red lines. And because both wavefronts have maxima at those locations, those two things add constructively, and wherever there is both wavefronts, you will have double the electric field. When you go ahead and you add the consideration of the minima of your wavefronts, we will denote them as purple as shown before, and once again along the optical axis we have red interfering with red and purple interfering with purple, and they will both add constructively. They will double in the positive direction and they will double in the negative direction. But what's interesting perhaps more interesting at this point, is the location where red interferes with purple, and that's where things will cancel out, provided that those two sources are of the same magnitude. And for this example, we can assume that they are. And now we'll allow those two wavefronts propagate, again highlighting that the points where the red and purple maxima and minima intersect moves along the propagation direction. For the definitions of constructive and destructive interference, we can say the following. Constructive interference happens when two waves are exactly coherent, and what that means is that the two waves line up, and what we have is maxima on top of maxima and minima on top of minima, and what that produces is higher maxima and higher minima in the resulting electric field or magnetic field. Destructive interference happens when the two waves are exactly anticoherent. What that means is they line up with minima and maxima interchanging, so they are 180 degrees out of phase. And once you have that, then they will perfectly cancel and you will produce a flat line. Of course, in reality, we won't have just those two examples of interference. It's not just constructive and destructive interference. We can define a whole swath of interference conditions, and they will basically produce different amounts of phase shifts between the two sinusoidals. But understanding the two edge cases that we present here is key for the rest of the discussion. Now let's look at the example of the Young's double slit. Thomas Young performed an experiment in 1801 that proved that light is a wave. And the way that he did that is he constructed one screen and he illuminated that with a beam of light very, very far away. And the very far away component of it was to ensure that the wavefronts from that source would be planar by the time that they reached the screen, and that would simplify the interaction of the wavefronts with those two slits. Those two slits acted as a secondary source that would each produce a spherical wavefront. Those two spherical wavefronts would then propagate and interact with the screen, where we can place a detector. And the premise behind the experiment was that if light is indeed a wave, then we will see an interference pattern on the screen, whereas if light is not a wave, then we will see a pretty flat distribution. Now let's look at some of the geometrical properties of the setup. The two slits are separated by length d. The two screens are separated by length L. We are making an observation at an arbitrary location of y along the second screen, and then we can name the top and the bottom slits as having R2 and R1 separation with that arbitrary location y. In addition to those variables, we'll also introduce r, which is the distance from the center of those two slits to the same arbitrary location y, and also angle theta. Now mathematically, the two spherical waves can be expressed as a divided by r1, a divided by r2, and then exponential e to the j beta r1 and e to the j beta r2. And in essence, they're the same, except for one operates on r1 and the other one operates on r2. Total intensity at the second screen will then be the magnitude square of the sum of those two waves. And this is something that you saw in a different lecture with Poynting vector being related to the magnitude square of the electric field plus some other constants, and this is why it's proportional to and not necessarily exactly equal to. Once we plug in the definitions of our spherical waves into U1 and U2, we can then do some further modifications by redefining R1 and R2 to be in terms of R, the central R that we introduced here, and delta R. This delta R is essentially this distance right here, which can be later related to d, the separation between the two slits, and the sine of the angle theta. And there'll be more on that in a little bit. Once we plug in those definitions, we can rewrite that calculation to produce exponentials with r plus delta r divided by 2 and exponential with r minus delta r divided by 2. As you can see here out front, we have a divided by r and a divided by r instead of a divided by r1 and a divided by r2. And this change is because it is safe to approximate r to be about the same between slit 1 and slit 2, but only when it comes to operating with the magnitude of your field, not the phase. Because if you can imagine propagating for a million wavelengths here and a million wavelengths here, it doesn't really matter if you propagate by a million wavelengths or if you propagate by 1.25. But if you make the same kind of approximation here, then it will essentially make you have absolutely no consideration of phase whatsoever, and you will not properly account for accumulation of phase. That's why it's appropriate to simplify this to r when you divide, but it's not appropriate to simplify it to r when you have an exponential. Further grouping terms, we can factor out e to the j beta r, and we can recognize the remaining exponentials as a cosine. In this case, it'll be 2 cosine of beta delta r divided by 2. Solving further, we can expand the magnitude. We'll get 4a squared divided by r squared cosine squared of beta delta r divided by 2. And then we can further identify this as a trig identity which talks about half angles and expand it into the full angle, and this will be equal to 1 plus cosine beta delta r divided by 2. What this means is that the intensity will indeed go through minima and maxima. Minima here, 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 and here, and then we'll have maxima along here. We can now take a closer look at the argument of cosine, beta delta r, and we can rewrite it as 2 pi divided by lambda, which is beta, and d sine theta, which is this little segment right there. And if you draw it out on a piece of paper, and you can convince yourself that that is indeed that separation right there. What we're then interested in is when will this argument of beta delta r give constructive interference for this term as a whole. At every 2 pi, cosine will produce 1. So this entire bracket contents will become unity. And conversely, when cosine's argument is negative pi or positive pi or 3 pi, this factor will go to 0. So by setting beta delta r equal to 2 pi n, we can figure out where the maxima are for our interference pattern. And to do that, we can make a few approximations. We can pretend that theta is small and then sine theta is equal to theta, and that means that it's simply y divided by L. Plug that in. We can then notice that both sides have 2 pi. We can cancel that out, and then we can rearrange this equation to be solved for y. And so what we ended up with is an equation that gives us the maxima locations along the screen. And because we're in control of D, we're in control of L, and we know what the wavelength of our light is, we can calculate those Y's pretty precisely. And what turned out is that Thomas Young's experiment worked in the sense that the predicted values for the separation and the actual values for those maxima right here matched, thereby proving that light is a wave. Later, similar experiments were performed for electrons, where the same kind of particle-wave duality was established, and even more recently now, where we have molecules that have on the order of thousands of protons, electrons, and neutrons, have also been shown to have particle-wave duality. And particle-wave duality is something that is inherent to everything in the universe and is something that should be appreciated. Finally, as far as tutorial topics, we will describe wavefronts, plane waves, and so on. And we will also calculate interference patterns, but that will only be limited to plane waves to keep our sanity. Thank you.